Good afternoon, everyone. Today I will talk about a conjecture proposed by Lenny Jones about the monogeneity of certain type of polynomial families. This result is based on a joint work with S. Kumar, where we prove that this conjecture is true. So before stating the conjecture, I will first recall what is monogeneity and why it is important in algebraic number theory. So if we have an algebraic number field K, we say that this field is monogenic if its ring of integers is generated by a single algebraic integer theta. So regarding the polynomials, if we have a monic irreducible polynomial fx with a root theta, if the ring of integers of q theta is z theta, then we say that that polynomial is monogenic. So if we have a monogenic polynomial, it gives us a monogenic field, but the converse is not true in general. So in monogenic fields, the arithmetic computations are simpler because the ring of integers is generated by a single element. So monogenic fields are very important. Now, our natural question is that if we have a monic irreducible polynomial fx with integer coefficients and a root theta, whether this field q theta, is it monogenic or not? So in general, it is a hard problem and there is no general criteria which is known that can classify that whether this field will be monogenic or not. So many mathematicians, what they do, they try to consider different type of polynomial families, and they from their root they try to construct the field q theta and then try to study the monogeneity of that particular field q theta. So in monogeneity, the discriminant is a important tool which can help us to characterize the given field as monogenic or non-monogenic. So the discriminant of a polynomial fx and the discriminant of the field k q theta, they are related by this formula. This quantity, which we called as an index of the field k, this gives us the size of the ring, like how far is the ring of integers from being monogenic. If this index is 1, then we say that our field is monogenic. So from this equation, we can easily see that if the discriminant of the polynomial is carefree, then the field will be monogenic. But the converse is not true. There are many monogenic polynomials where the discriminant is not carefree, but they are monogenic. So now this was the conjecture proposed by Lenny Jones. He considered this family of polynomials, and certain GCD condition was satisfied. He conjectured that this polynomial family will be monogenic if and only if this expression, it will be carefree. So this the criteria was very clean that the monogeneity of this polynomial family depends upon the carefreeness of this term. So we proved this theorem in which we consider this polynomial family. Here we take a to be any non-zero integer, and the original conjecture a was a prime number. So we prove that this family of polynomial will be monogenic if two conditions are satisfied. First, a is carefree, and second, this term, this expression is carefree. So if a is a prime number, this gives us the conjecture of Jones. So the conjecture of Professor Jones follows from this theorem and is a particular case of this theorem. And the key idea behind the proof of this theorem was the Dedekind criteria, which gives us a tool how we can relate the index of a polynomial, like which primes divide the index of a polynomial, and the factorization of that polynomial modulo that prime. So using Dedekind criteria, we try to classify the primes which can divide the index, and we got this result. Now the other question is whether can we remove this GCD condition or not. So the answer is no. If we take this polynomial fx, for this this polynomial is monogenic, but the discriminant, this doesn't satisfy the scarce-freeness term. So the condition that GCD and of n and MB should be 1, this we cannot remove. And these are the references, and thank you. I'm happy to take any questions.